Hello everyone. Have you ever wondered how a massive ship floats effortlessly on water while a small iron nail sinks instantly? Or why lifting a stone feels so much easier inside water than in air? The secret lies in one of the oldest and most elegant discoveries of physics, Archimedes' Principle. When a body is immersed in a liquid, it pushes some of that liquid aside. We say it displaces liquid. And the liquid, in turn, pushes back on the body with an upward force called upthrust. The magnitude of this upthrust is equal to the weight of the displaced liquid. This simple law governs why objects float or sink. Archimedes' principle can be stated formally like this: when a body is immersed partially or completely in a liquid, it experiences an upthrust equal to the weight of the liquid displaced by it. This upthrust is not dependent on what the body is made of, it depends only on the amount of fluid displaced. That's why a hollow iron ship floats while a solid iron nail sinks. Another important point: Archimedes' principle applies not only to liquids but also to gases. That's why balloons filled with helium or hot air rise in the atmosphere. They displace air which has weight. Now let's look at why this happens. Liquids exert pressure in all directions, and this pressure increases with depth. That's given by the formula P equals H into rho into G. The bottom of a submerged body is at a greater depth than the top, so the pressure at the bottom is larger. This means the upward force on the bottom is greater than the downward force on the top. The difference between these forces is the net upward thrust, which is equal to the weight of the liquid displaced. Archimedes' principle also explains why bodies appear lighter inside water. Suppose a stone weighs W in air. When we immerse it in water, it appears lighter, its apparent weight is smaller. The difference, W minus W apparent, is exactly equal to the buoyant force. This is why carrying a heavy bucket of water feels easier while it's still inside the well, but heavier as soon as it comes out. The upthrust helps us inside the water, but vanishes outside. This principle has wide-ranging applications in science and daily life. It's used to design huge ships and submarines so they can float safely despite their weight. It explains how hydrometers measure density of liquids. It also tells us why balloons and blimps rise in the sky, because the buoyant force of displaced air is greater than their weight. From swimming and diving to naval engineering and aviation, Archimedes' principle is everywhere around us. Let's solve a simple numerical to verify Archimedes' principle. A stone weighs 50 newtons in air and only 30 newtons when immersed in water. What is the upthrust on the stone? Step 1. Upthrust equals loss in weight. That is, 50 minus 30 equals 20 newtons. Step 2. By Archimedes' principle, this upthrust must equal the weight of displaced water. So the stone displaces 20 newtons of water. This proves that the apparent loss in weight is exactly equal to the weight of displaced liquid. So to wrap this up, Archimedes' principle tells us that any body immersed in a fluid experiences an upward force equal to the weight of fluid it displaces. This explains floating, sinking, and the concept of apparent weight. Whether it's a swimmer in a pool, a ship in the ocean, or a hot air balloon rising in the sky, the same principle is at work. I hope you now have a clear picture of why buoyancy exists and how Archimedes' principle beautifully connects displacement with upthrust. See you in the next session, where we'll take this further into the laws of flotation.